We get our feet wet with the work and work energy theorem. We've thought about the case where we have a force that's constant in magnitude and direction. And our prototype for that would be the force of gravity. So if we're talking about motion with displacements that are small compared to the size of the Earth, then the acceleration due to gravity is essentially constant. So we have the same magnitude and it's always pointing down towards the center of the Earth. And what do we do if that's not the case? What if we have an object acted on by a force that changes? Well, you go through, and if this is the plot of our force in one dimension, and we're concerned with the interval between the final and the initial position, then what we're trying to do is add up all of the area underneath this curve between those two bounding points. And you could imagine trying to get the area under this curve by making a bunch of rectangles. And you could imagine making a rule that I want the middle of the rectangle to match up with the value of the function of the middle of each of these little subintervals. And then clearly what would happen is sometimes I'm a little too high, sometimes a little too low. But if I make more and more and more rectangles, I'm going to do a better and better job. And if I let this interval size, delta x, shrink to an infinitesimal size, dx, then what I'm actually doing to get the area under this curve from x initial to x final is I'm integrating the function. Okay. So the work over an interval from x1 to x2 is the integral of the force over dx. So integrate the function f of x with respect to x, starting from x1, ending at x2. That's what we mean by work. That is true general. Doesn't require any special symmetry for the force, doesn't have to be constant, doesn't have to be a fixed direction, could be anything. And we live in a three-dimensional world, so how do you extend this to three spatial dimensions? Well, I get the work by doing the integral of the differential of work. And that differential of work, dw, means I'm integrating the force dot product with a differential in coordinate position, dr vector. And I start from some initial point in three-dimensional space, and I'm going to end at some final point in three-dimensional space, R2. This scalar product is going to have, if it's in Cartesian components, it has a part along x, a part along y, and a part along z. I have to treat all of those equally. So the integral of dw is going to be partly made up of the x component of the force integrated over x, the y component of the force integrated over y, and then the z component of force integrated over z. So if you need to go back to some fundamental equation for what is the work for a general force in three spatial dimensions, you can go all the way back to this. The work will be equal to this three-dimensional integral starting from position 1, ending at position 2. What I'm integrating is the dot product of the force with the coordinate differential. Okay. I don't believe you're ever going to have a case where you need that in this class. In future life, you very well might. But that is the most fundamental level, what we mean by work for the most general expression of the force. Okay, let's try an example. A 12,500 kilogram truck is going to be accelerated from rest by a net force that decreases linearly with the distance traveled. So plot of force versus distance traveled is that straight line. So it's 1,300 newtons of force at the starting point, and it's 0 newtons of force after 150 meters. Okay. So using this plot and the work energy theorem, what is the approximate speed of the truck when the force is removed? So when you get to 150 meters, the force goes to 0. How fast is the truck moving? Assume it started from rest, as stated in the problem. So spend a little time trying to work that out, and we'll go over the answer in just a little bit. Okay, so it is 12.5 meters per second, so about 25 miles per hour. Work energy theorem is giving us that the work is the change in kinetic energy, so that's K final minus K initial, but K initial was 0 because the truck started at rest. All right, so the area under the curve in this case is really simple because it's just a triangle. So I'm trying to calculate the area of a triangle in this force versus distance space. So that gives me work. It's going to be a half base times height. Height is 1,300 newtons. And then base as it goes 150 meters before the force falls to 0. And then on the right-hand side of the work energy equation, we have the final kinetic energy. So that gives me another factor of a half from a half mv squared. Mass of the truck was 12,500 kilograms. And then the thing we're trying to solve for, V final squared. V final squared. So we can get rid of the factor of a half. 1,300 times 150 divided by 12,500, all square root is going to give you just a little bit shy of 12.5. So it rounds up to 12.5. All right, let's try the next question. Talk about a spring. So you could have just a general force that depends upon position. We're also going to think about a specific case for a force that obeys Hooke's law. And Hooke's law is a remarkably useful force. There are going to be lots of occasions in physics where even if the force doesn't exactly obey Hooke's law, we'll just divide up the domain into small enough intervals that over each interval, to a good approximation, the force is linear in position. So make a piecewise linear function out of some more complicated function. That's how good Hooke's law is. Turn yourself upside down and inside out to make the problem look like Hooke's law. So Hooke's law, as a general statement, is I take some spring and I displace the end of it. If the spring force obeys Hooke's law, that tells me that the more I displace the end, the stronger the spring is going to pull back. And this minus sign in Hooke's law is just there to remind us that if I stretch a spring out, it pulls back. If I push a spring in, it's going to try to expand back out. So relative to whatever the equilibrium length of the spring was, the force exerted by the spring is opposite the direction of the displacement. Okay, so don't get hung up on the minus sign. It's not that big a deal. It's just there to remind us how a spring is going to behave. If I agree that we're only going to worry about displacements at the end of the spring along the length of the spring, and this is no longer a vector statement in 3 spatial dimensions, but it's a 1-dimensional statement. So the force of the spring exerts is minus kx, what we normally think of as Hooke's law, and x is measured relative to the equilibrium length of the spring. So what we had previously, the work done by the spring is going to be equal to the integral of this force integrated with respect to x. So the Hooke's law force is minus kx, integrated with respect to x. We start from some initial position and at some final position. So k is a constant, I can pull it out. So I'll have minus k over 2. The integral of x dx is a half x squared. When we evaluate that between the upper bound and the lower bound, I've got a minus sign out front, so we flip those 2 terms around. So the work done by a spring is a half k. It is going to be initial position squared minus final position squared. For the work done by a spring, since the force is linear in position, this work done by a spring gets much larger, much quicker as x gets bigger. So it's a quadratic function. All right, let's try it out. Our work done by a spring expression. The spring-loaded toy dart gun is used to shoot a dart straight up into the air. The dart reaches a maximum height of 24 meters, so pretty high up. Same dart is shot straight up a second time from the same gun, so same spring constant, but this time the spring is compressed only half as far before firing. How far up does the dart go this time? We neglect friction, and we assume that it's an ideal spring, so don't have to worry about the mass of the spring, and it does actually follow Hooke's law. All right, so try to work that out, and we'll compare answers in just a second. All right, when fully compressed, we're able to shoot the dart up 24 meters. If the compression is only half as big, then the work that the spring can do is going to be 1/4 as big. And so that is going to amount to a work done by gravity that is 1/4 as big when the dart stops at its highest point for an instant. So if I could do enough work from the spring to raise it 24 meters with the full compression of the spring, with half a compression of the spring, and I can only do 1/4 as much work. So it's going to be only 6 meters high. So still high enough to get the ceiling, but much less than 24.